Let us continue exercise 6.2. Question number 8. Find the values of x for which y equal to x times x minus 2 the whole square is an increasing function. This is a polynomial. We can write this as x square times x minus 2 the whole square. Let us differentiate. Dy by dx is equal to, we will use product rule, u and v. U dash is 2x times v plus x square times derivative of v term is 2 times x minus 2 into 1. We will take the common factors out. 2x times x minus 2 is common. We get x minus 2 from the first term and x from the second term. 2x times x minus 2, 2x minus 2. 2 is common in the last term. 2 2s are 4. 4x times x minus 2 times x minus 1. We will equate this to 0 and get the critical points. We get x equal to 0, x equal to 2 and x equal to 1. 3 critical points are there. Since this is a polynomial, the domain is minus infinity to infinity. Let us write the critical values. We have to write them in ascending order. 0, 1, 2. We have 4 intervals. Since the word strictly is not mentioned in the question, we can include the critical values in the intervals. So the first interval is minus infinity to 0, closed at 0, closed interval 0 to 1, closed interval 1 to 2, and closed at 2 to infinity. So we have included the critical values in these intervals because in the question we don't have the word strictly. Now we will draw the table. We will write the intervals minus infinity to 0, 0 to 1, 1 to 2, 2 to infinity. Again I am repeating, since the word strictly is not mentioned, we have included the critical values in these intervals. When we have closed intervals, we should not use the critical values for checking the sign of dy by dx, because at those values derivative will be 0. We won't be able to decide whether it is greater than 0 or less than 0. So we should not use the critical values for checking the sign of dy by dx. From the first interval, we will substitute minus 1 for checking. We should not use 0 to check the sign of f dash because 0 is a critical value. Now we will check the sign of dy by dx. We will check in this factorization step dy by dx at minus 1. 4 is positive, x is minus 1 which is negative, minus 1 minus 2 is negative, minus 1 minus 1 is also negative. Product of 3 negative terms is less than 0. Therefore, f is decreasing in this interval. From the second interval, we will substitute half. Dy by dx at half. 4 is positive, x is positive, half minus 2 is negative, half minus 1 is also negative. Therefore, the product is greater than 0. The function y is increasing in this interval. From the third interval, we will take 1.5, which is 3 divided by 2, dy by dx at 3 by 2. 4 is positive, x is positive, 3 by 2 minus 2 is negative, 3 by 2 minus 1 is positive. Therefore, the product is less than 0. The function y is decreasing in this interval. Since we have included the critical points in these intervals, remember we should not use the word strictly. For the last interval, we will substitute 3 and check dy by dx at 3. 4 is positive, x is positive, 3 minus 2 is positive, 3 minus 1 is also positive. Product is greater than 0. Therefore, f is increasing in this interval. We have to find the values of x for which the function is an increasing function. Therefore, y increases in closed interval 0 to 1, union closed interval 2 to infinity. Question 9. Prove that y equal to 4 sin theta divided by 2 plus cos theta minus theta is an increasing function of theta in the closed interval 0 to pi by 2. So, the domain is given as the first quadrant, closed interval 0 to pi by 2. Let us differentiate this function, and y is a function of theta, so we will get dy by d theta. We will use quotient rule. U by v the whole dash is u dash v minus u v dash divided by v square. 4 times derivative of sin theta is cos theta into v 2 plus cos theta minus u is 4 sin theta into derivative of the denominator. Differential of 2 is 0 and differential of cos theta is minus sin theta. Use brackets because of the negative sign, divided by 2 plus cos theta the whole square minus derivative of theta with respect to theta is 1. Let us take LCM. 2 plus cos theta the whole square. We will simplify the numerator. 8 cos theta plus 4 cos square theta minus into minus is plus 4 sin square theta minus of 2 plus cos theta the whole square. Let us expand and write 4 plus cos square theta plus 4 cos theta. 8 cos theta plus 4 is common in the next two terms. We will get sin square theta plus cos square theta, which becomes 1. Here we will distribute this negative sign, minus 4 minus cos square theta minus 4 cos theta divided by 2 plus cos theta the whole square. We get 4 cos theta minus cos square theta divided by 2 plus cos theta the whole square. And in the numerator cos theta is common. We get 4 minus cos theta divided by 2 plus cos theta the whole square. Look at this dy by d theta term. Cos theta 4 minus cos theta divided by 2 plus cos theta the whole square. Look at the denominator, 2 plus cos theta the whole square. Because of whole square, we can say that it is always greater than 0, which is positive. And even if theta is 90 degrees, cos 90 will be 0. 2 plus 0 is 2 square, which is 4. So, always it is positive. And then 4 minus cos theta. We know that in the first quadrant, cos theta is less than or equal to 1 and greater than or equal to 0 in the given domain, closed interval 0 to pi by 2. Therefore, 4 minus cos theta is also greater than 0, which is positive. Now, the next term, cos theta. In the given domain, closed interval 0 to pi by 2, this cos theta can take the values which are greater than or equal to 0. It can be equal to 0. Cos 90 is 0, right? So, to find the critical points, we equate it to 0. So, we get cos theta equal to 0 or 4 minus cos theta equal to 0, from which we get cos theta equal to 4, which is not possible because cos does not take the values which are more than 1. So, cos theta equal to 0 gives the answer theta equal to pi by 2. So, this critical value is already included in that domain, and we cannot split the domain into sub-intervals because only one critical point we got, which is pi by 2. So, we cannot split the given domain further. So, we will keep the whole given domain closed interval 0 to pi by 2 because we are not able to split it into sub-intervals. We did not get any in-between value. Now, we will check whether dy by d theta is positive or negative in this interval. So, you can use this method to check the sign, or you may substitute some value of theta. We will take theta as 0. It is closed at 0. So, we can use the value 0, but we cannot use the value pi by 2 because f dash will be equal to 0. Do not use critical values for checking. 0 is not a critical point. So we can use this value. We will substitute in f dash cos 0. Cos 0 is 1. 4 minus cos 0, which is 1, divided by, it is already positive anyhow, cos 0 is again 1. So 1 into 3 divided by 3 square, which is 9, which is positive. Since the critical value pi by 2 is included in this interval, I can say that in the given domain closed interval 0 to pi by 2, dy by d theta is greater than or equal to 0, because at pi by 2 it becomes 0. Therefore, y is an increasing function in closed interval 0 to pi by 2. Since the critical value pi by 2 is included in this interval, we cannot use the word strictly. Question number 10. Prove that the logarithmic function is strictly increasing on open interval 0 to infinity. Let us find f dash of x. Differentiation of log x is 1 upon x. We cannot equate this to 0 because we will get 1 equal to 0. That means f dash doesn't become 0 at all. Now, if you see the interval, open interval 0 to infinity, for all values from this interval, 1 by x is greater than 0. For all x belonging to open interval 0 to infinity. Therefore, f of x is strictly increasing on open interval 0 to infinity. Question 11. Prove that the function f given by f of x equal to x square minus x plus 1 is neither strictly increasing nor strictly decreasing on open interval minus 1 to 1. Let us find f dash of x, which is 2x minus 1. We will equate the first derivative to 0. We get x as half. The given domain is minus 1 to 1 and the critical value is half. So we get two intervals. Open interval minus 1 to half and open interval half to 1. Since the word strictly is mentioned in the question, we should not include the critical value half. So in the first interval, let us check the sign of f dash by substituting a value from this interval. We will take 0. F dash is 2x minus 1. 2 times 0 minus 1 is minus 1, which is negative. Therefore, f strictly decreases in this interval. Now let us check for the next interval. Half is 0.5. Let us check with 0.6. 2 times 0.6 is 1.2 and minus 1, which is 0.2, positive. Therefore, f strictly increases in this interval. So if you combine these two intervals, minus 1 to 1, we can say that the function neither strictly increases nor strictly decreases on minus 1, 1. Remember, in an interval, if a function strictly increases as well as strictly decreases, say, we conclude that it is neither strictly increasing nor strictly decreasing in that interval. Question 12. Which of the following functions are strictly decreasing on open interval 0 to pi by 2? A subdivision, f of x is cos x and the interval is open interval 0 to pi by 2. Let us find f dash, which is minus sin x, and if we equate f dash to 0, we will get x equal to 0, which is not included in the domain. So we don't get a critical value in this given interval. Now we will check whether f dash is positive or negative in the given interval. When x lies between 0 and pi by 2, we know that sin x is greater than 0. Therefore, minus sin x is less than 0. F dash of x is less than 0. Therefore, f of x is strictly decreasing on open interval 0 to pi by 2. B subdivision, f of x is cos 2x. The interval is the same, 0 to pi by 2. Let us find f dash of x, which is minus sin 2x into derivative of 2x is 2. Now here the domain is open interval 0 to pi by 2. This is for x. The condition for 2x will be, let us multiply the inequality throughout by 2. 0 times 2 is 0. 2 times pi by 2 is pi. So this is first and the second quadrants. We know that in these two quadrants, sin 2x will be greater than 0. Sin 2x will be 0 only when 2x is 0 or 2x is pi, but those two values are not included in this interval. Therefore, sin 2x is strictly greater than 0. Therefore, f dash of x, which is minus 2 times sin 2x, because of this negative sign, it is strictly less than 0. Therefore, f of x is strictly decreasing on open interval 0 to pi by 2. Now, C subdivision, f of x is cos 3x and the given domain is open interval 0 to pi by 2. Let us find f dash of x, which is minus sin 3x into 3x has to be differentiated, which is 3. Now look at the given domain, 0 less than x less than pi by 2. Here we have 3x. Let us multiply the whole inequality by 3. 0 times 3 is 0. 3x less than 3 pi by 2. 0 to 3 pi by 2 is first three quadrants. 0 to 3 pi by 2. We know that in the first quadrant sin is positive, in the second quadrant also sin is positive, but in the third quadrant it is negative. That is 0 less than 3x less than pi, sin 3x will be positive, and in the interval pi less than 3x less than 3 pi by 2, sin 3x is negative. Let us divide by 3. Therefore, in the interval 0 to pi by 3, f dash of x is negative, and in the interval pi by 3 to pi by 2, f dash of x will be positive because of that minus sign, minus 3. So, combining these two intervals, we can say that f of x is neither strictly increasing nor strictly decreasing on 0 to pi by 2. D subdivision, let f of x be tan x and the interval given is 0 to pi by 2, open interval. F dash of x is secant square x. We know that secant x does not take the value 0 at all for any value of x, and we have square for this function. So, it is always greater than 0. Therefore, f of x is strictly increasing on open interval 0 to pi by 2. Question 13. On which of the following intervals is the function f given by f of x equal to x power 100 plus sin x minus 1 strictly decreasing? Let us calculate f dash of x, which is 100 times x raised to 99 and derivative of sin x is cos x. By equating it to 0, we won't be able to solve for x. So, in the given intervals, we will check the sign of f dash. The first interval given is open interval 0, 1, 0, pi by 2. Decimal value of pi by 2 is 3.14 divided by 2, which is 1.57. So the given interval is 0 to 1. Here 0 to 1, the angles are given in radians, which is in the first quadrant. Therefore, cos x is greater than 0 in the given interval 0 to 1, and 100 times x power 99 will be positive because all values are positive in this given interval. Therefore, f dash of x is strictly greater than 0 in the given interval. Therefore, f of x is strictly increasing on 0, 1. Let us check in the next interval b, open interval pi by 2 to pi. Pi by 2 value is 1.57 radians and pi is 3.14 radians. So it is the second quadrant. And in the second quadrant, we know that cos becomes negative. And negative values of cos x are between -1 and 0. But look at the first term. 100 times x power 99 will be a very large value, whatever value you take from this interval. For example, let us take 2 from the second quadrant. 100 times 2 power 99 is going to be a very large number when we compare it with this cos value. In this interval, 100 times x power 99 is going to be very large. Definitely it will be more than 100 because x is greater than 1 in this interval. And when we compare this value with the second term, that is cos x value, cos x is a very small negative value. The final answer is going to be a positive number. Therefore, f dash of x in this interval is greater than 0. Therefore, f of x is strictly increasing on open interval pi by 2 to pi. C subdivision, the given interval is 0 to pi by 2, which is the first quadrant. We know that in the first quadrant, cos x is positive, the second term is positive, and the first term is also positive because all are positive values in this interval. So in this interval, both the terms are positive. Therefore, f dash of x is greater than 0. Therefore, f of x is strictly increasing on open interval 0 to pi by 2. Look at the question. The question is asking for the intervals in which it is strictly decreasing. But in the first 3 intervals, the function is strictly increasing. Therefore, the answer is D subdivision, none of these. Question 14. Find the least value of a such that the function f given by f of x equal to x square plus ax plus 1 is strictly increasing on the open interval 1 to 2. Let us write f dash of x, which is 2x plus a, and it should be greater than 0 for strictly increasing function. And look at the domain. It is open interval 1 to 2. So, x lies between 1 and 2. Let us multiply the whole inequality by 2. So, 2 times 1 less than 2x less than 2 2s are 4. We will add a throughout. 2 plus a less than 2x plus a less than 4 plus a. For the function to be strictly increasing, these two quantities should be strictly greater than 0. 2 plus a should be greater than 0. 4 plus a also should be greater than 0. From this we get a greater than -2. From this we get a should be greater than -4. The common solution is the final answer. -4 and -2. The first condition is a greater than -2, all these real values. And the second condition is a greater than -4, all these real values. The common solution is the final answer. So we conclude that a should be greater than -2. Therefore, the least value of a is minus 2. We have written here a should be greater than minus 2. How come we are saying that the least value should be minus 2? We know that x belongs to the open interval 1, 2. Here x cannot take the value 1. Let us take x as 1.000001. F dash of x is 2x plus a and it should be greater than 0. 2 times this x value will be 2.000001, and if we take a as minus 2, this difference is going to be positive. Even if we take minus 1, the difference will be positive, but we have to find the least value of a. Therefore, the least value of a is equal to minus 2. Question 15. Let I be any interval disjoint from closed interval minus 1 to 1. Prove that the function f given by f of x equal to x plus 1 upon x is strictly increasing on I. And the given interval is disjoint from closed interval minus 1 to 1. So, disjoint from minus 1 to 1 means other than these values, that is minus infinity to minus 1 and 1 to infinity. In the given interval disjoint from minus 1 to 1, minus 1 and 1 are included. So, in the domain minus 1 and 1 are not included. Open intervals at minus 1 and 1. Let us find f dash of x. 1 plus derivative of 1 upon x is minus 1 upon x square, that is taking 1 by x as x raised to minus 1. Using n into x raised to n minus 1 formula, we get minus 1 x raised to minus 2, which is minus 1 upon x square. We get 1 minus 1 upon x square. We can check the sign of f dash by taking values from each one of these intervals, or we can take LCM. For the function to be strictly increasing, we know that f dash is strictly greater than 0, and we know that the denominator is always greater than 0, and x cannot take the value 0, 0 is not there in its domain. Therefore, x square minus 1 should be greater than 0, that is x square is strictly greater than 1. Therefore, x should be greater than 1 and less than minus 1. That is nothing but the given domain. In both these intervals, f dash is strictly greater than 0. Or as I said, you can check in each interval. We can substitute minus 2 from this interval in f dash. 1 minus 1 divided by 4, which is positive, and from the second interval we will take 2. Let us check the sign of f dash. The same answer we will get. Here also it is greater than 0. In both the intervals, f dash is greater than 0. Therefore, we conclude that f strictly increasing on the given interval I. Question 16. Prove that the function f given by f of x equal to log of sin x is strictly increasing on open interval 0 to pi by 2 and strictly decreasing on open interval pi by 2 to pi. Let us find f dash of x. We have to apply chain rule. Derivative of log is 1 upon sin x and derivative of sin x is cos x. So, we get cot x. If we equate the first derivative to 0, we get x equal to pi by 2, and pi by 2 is not included in these intervals. Therefore, in the first interval 0 to pi by 2, f dash of x is strictly greater than 0. Therefore, f of x is strictly increasing on open interval 0 to pi by 2. Now, let us check for the next interval, pi by 2 to pi. Again, the critical value pi by 2 is not there in this interval. And in the second quadrant, we know that f dash is less than 0. Therefore, f of x is strictly decreasing on the open interval pi by 2 to pi. Question 17. Prove that the function f given by f of x equal to log of cos x is strictly decreasing on open interval 0 to pi by 2 and strictly increasing on open interval pi by 2 to pi. It is similar to the previous question. Let us do this question with the absolute value sign. We will take f of x as log of absolute value of cos x. If there is no absolute value sign, you have to follow the same steps as we did the previous question. Now let us see how to do with the absolute value sign. Let us do for the first interval. This is the first quadrant. We know that in the first quadrant cos x is positive. Therefore, we can remove the absolute value sign. As it is positive in this interval, we get f of x is equal to log of cos x. Now we will differentiate. F dash of x is, chain rule has to be applied. Derivative of log is 1 upon cos x into derivative of cos x is minus sin x. We get minus tan x. We know that in the first quadrant tan x is greater than 0. 0 and pi by 2 are not included, so there is no problem. Therefore, minus tan x will be less than 0 for every x belonging to the given interval. Therefore, f of x is strictly decreasing on open interval 0 to pi by 2. Now let us check for the second interval pi by 2 to pi. This is second quadrant. In the second quadrant, we know that cos x is negative. Therefore, f of x becomes log of, to remove the absolute value sign, we have to write minus sign. It becomes minus cos x, so that minus cos x will be positive. Now let us find f dash of x. Derivative of log is 1 upon minus cos x into derivative of minus cos x is minus of minus sin x. Here also we get minus tan x. But in the second quadrant, tan x is negative. Therefore, minus tan x will become positive in pi by 2 to pi. Pi by 2 and pi are not included. Tan is not defined at pi by 2 and tan is 0 at pi. Both are not included in this interval. So, we can say that minus tan x is strictly greater than 0 in the second quadrant. Therefore, f of x is strictly increasing on the given interval pi by 2 to pi. Question 18. Prove that the function given by f of x equal to x cube minus 3x square plus 3x minus 100 is increasing in R. Let us find f dash of x, which is 3x square minus 6x plus 3. We will factorize. 3 is common and this can be written as x minus 1 the whole square. And look at this function. It is always positive. 3 is a positive number. X minus 1 the whole square is also positive. So, we can say greater than 0, and at x equal to 1, it becomes equal to 0. Therefore, f dash of x is greater than or equal to 0. Therefore, we can say that f of x is increasing in R. We cannot say strictly increasing because f dash of x becomes 0 at x is equal to 1. So, when f dash is greater than or equal to 0, we say that the function is increasing. Question 19. The interval in which y equal to x square times e raised to minus x is increasing is. The intervals are minus infinity to infinity, minus 2 to 0, 2 to infinity and 0 to 2. Let us find dy by dx. We have to apply product rule. 2x times e raised to minus x plus x squared times derivative of e power minus x is e power minus x into minus 1. We will take the common factors out. X times e power minus x, we get 2 minus x. We will equate the first derivative to 0. We get x equal to 0. We know that exponential function never takes the value 0. X equal to 2. So, we have two critical values, x equal to 0 and x equal to 2. dy by dx is x times 2 minus x divided by e raised to minus x can be written as e raised to x in the denominator. Now, we know that the denominator is always greater than 0. Exponential function is always a positive function. Now, it all depends upon the value of x into 2 minus x. So, the intervals will be minus infinity to 0, 0 to 2, 2 to infinity. Let us check in the first interval. We will take the value minus 1. It is enough if we check the numerator, x into 2 minus x. X is minus 1. 2 minus of minus 1 becomes 3, which is negative. And in the interval 0 to 2, we will check with the value 1. Let us check the numerator of dy by dx because we know that denominator is positive already. So, 1 into 2 minus 1. This is greater than 0. And from the third interval, we will take the value 3. Let us check the numerator of dy by dx. 3 times 2 minus 3 minus 1, which is negative. So, in the first interval, the function is strictly decreasing, and in the second interval, it is strictly increasing, and in the third interval, it is strictly decreasing. Now, let us answer the questions. The first interval is minus infinity to infinity. We have decreasing as well as increasing in the whole interval r. Therefore, we conclude that the function neither increases nor decreases. Now, let us see the second interval, which is minus 2 to 0. Minus 2 to 0 is the sub-interval of minus infinity to 0. In the interval minus infinity to 0, it is a decreasing function. So, in the interval minus 2 to 0 also, y decreases. Actually, we can say strictly decreasing. If the function is strictly decreasing, no harm in saying decreasing. Then C subdivision, 2 to infinity. 2 to infinity is the third interval. Look at the number line. In that interval, it is strictly decreasing. We can say y is decreasing. Now, D subdivision, the given interval is 0 to 2. See the number line? In the interval 0 to 2, it is a strictly increasing function. If it is strictly increasing, no harm in saying increasing. Therefore, the answer is D. Let us do example 12. Find the intervals in which the function given by f of x equal to sin 3x, x belonging to the closed interval 0 to pi by 2 is increasing or decreasing. Let us find f dash of x. Derivative of sin is cos 3x into derivative of 3x is 3. We will equate the first derivative to 0. Cos 3x is 0. That is 3x will be pi by 2, 3 pi by 2, etc. But we have to see the values which are in the given domain. Therefore, we get x as pi by 6 and pi by 2, that is dividing by 3. So, these are the two critical values. The given domain is 0 to pi by 2 and it is a closed interval, and we have pi by 6. Since the word strictly is not mentioned in the question, we can include the critical values in the intervals which we are going to write. 0 to pi by 6 and pi by 6 to pi by 2. 0 is already included in the domain. Now we will check the sign of f dash in these intervals. Let us check for the first interval. we cannot use critical value for checking the sign of f dash. Pi by 6 is a critical value. Don't substitute pi by 6 and check, but we can substitute 0. 0 is not a critical value, so we can use that value. We get 3 times cos 0. Cos 0 is 1 and it is greater than 0. Therefore, f of x is increasing in this interval. Now let us check for the next interval, pi by 6 to pi by 2. Here both are critical values, pi by 6 as well as pi by 2. So we cannot substitute these values for checking the sign of f dash. We will take pi by 3 from this interval. 3 times cos 3 times pi by 3, which is pi, and cos pi is minus 1. 3 times minus 1 is minus 3, which is less than 0. Again, we cannot use the word strictly because we have included the critical values pi by 6 as well as pi by 2. Therefore, f of x is decreasing in this interval. Now we will do example 13. Find the intervals in which the function f given by f of x equal to sin x plus cos x, 0 less than or equal to x less than or equal to 2 pi is strictly increasing or strictly decreasing. Let us find f dash of x. Derivative of sin x is cos x and derivative of cos x is minus sin x. We will equate the first derivative to 0 to find the critical values. Cos x is equal to sin x. We will divide both sides by cos x. We get 1 equal to tan x. Tan x is positive in the first and in the third quadrants. So we will get two answers because the domain is 0 to 2 pi, all 4 quadrants. And in the first quadrant, the angle is pi by 4 at which tan becomes 1. And third quadrant angle will be pi plus pi by 4, which is 5 pi by 4. Therefore, x is pi by 4 and 5 pi by 4. These are the critical values. Here we may go wrong by writing only one value pi by 4. See the domain, it is 0 to 2 pi. So we have to write the answers from all 4 quadrants so that tan x is equal to 1. We will draw the number line. The given domain is 0 to 2 pi and we have got two critical values pi by 4 and 5 pi by 4. Let us draw the table. We will write the intervals. Here in the question we have to check whether it is strictly increasing or strictly decreasing. So we should not include the critical values in the intervals. The intervals are 0 to pi by 4, pi by 4 to 5 pi by 4, 5 pi by 4 to 2 pi. 2 pi and 0 should be included because the domain is 0 less than or equal to x less than or equal to 2 pi. 0 and 2 pi are already there in the domain. Only at the critical values we have to write the open intervals. We will write the intervals 0 to pi by 4, pi by 4 to 5 pi by 4, 5 pi by 4 to 2 pi, closed at 2 pi. Look at the number line. For the first interval, we will substitute pi by 6 and check, or we can substitute 0 also. 0 is included in the domain. And from the second interval, we will check at pi by 2 or pi. And from the third interval, we will take 3 pi by 2 for checking. F dash of 0, and we have to substitute in cos x minus sin x. We should not substitute in tan x and check because we got tan x only after equating it to 0. F dash of 0, cos 0 is 1, sin 0 is 0. The answer is 1, which is greater than 0. Therefore, f strictly increases in this interval. Now for the second interval, we will substitute pi and check. Cos pi is minus 1 and sin pi is 0. Therefore, the answer is less than 0. F of x strictly decreases in this interval. Now, for the third interval, we will use 3 pi by 2. Cos 3 pi by 2 is 0 and sin 3 pi by 2 is minus 1. So, minus of minus is plus, greater than 0. Therefore, f strictly increases in this interval.